Okay, so today our speaker is David Galban, and he will be giving talk on cohomology and representation theory of Lie superalgebras.
Okay. So I'll just pull up the slides first. So yeah, first of all, I'd like to thank everybody for coming today. All right. And so yeah, like Tamana said, my talk is going to be on the cohomology and representation theory for Lie superalgebras. Right. And before I start, I just want to give an outline of what the talk is going to be like. So there's going to be two main sections of the talk. The first is essentially material that I covered in the algebra seminar last year. It's going to be on just Lie superalgebra cohomology itself. So looking at the cohomology of essentially an analog to the nilpotent radical for Lie superalgebras. So essentially, I'm going to start by describing my motivation and going over what Kostant theorem states for the ordinary Lie algebra case. And then I'm going to show how we can calculate similar cohomology groups for small dimensions or for small degrees. First, using a Hochschild-Serre type spectral sequence for each of the families of the Lie superalgebras, and then doing some sample cohomology calculations in the first and second degrees. The second part of my talk is going to be on new material. It's going to be essentially on sheaf cohomology for Lie supergroups. And so I'm going to start off by defining some spectral sequence constructions. So two main ones that I'm going to use. And I'm going to use those to show how we can prove analogues for Kempf's vanishing theorem and for the Borel-Baudet theorem for sufficiently large weights. And then I'll conclude, if I have time, with some calculations for the H1 lambda case. All right, so to begin with the first section, we'll start off with what Kostant's theorem states for the ordinary Lie algebra case. So if G is a semi-simple Lie algebra over C, then what Kostant's theorem tells us is that the kth cohomology HK of U, where U denotes the nilpotent radical, comma lambda mu, we can just write that as the direct sum over all W in the Bio group of length K of L of W dot mu, where that's denoting the dot action of W on mu. And then L of W mu is just an irreducible finite dimensional module of highest weight W dot mu. So it turns out that this is going to be part of a larger picture where in category OJ, there exists this isomorphism between these X groups on the left and these Hom sets on the right. And it's going to be a deep result, in fact, that these X groups can be computed via Cauchy-List polynomials. Right. So moving on from the ordinary algebra case to the superalgebra case, we're just going to begin by defining a Lie superalgebra to be a Z2 graded vector space, so G0 direct sum G1, with a bilinear operation called the superbracket satisfying the following axioms. And so this first one is essentially an analog to the anti-symmetric property of the ordinary bracket, where we're just multiplying by this factor of -1 raised to a power of the parity of A and parity of B, where by parity we just mean 0 if it's in G0, 1 if it's in G1, and then maybe if it's not in either, we'll just extend linearly. And then we have this analog of the Jacobi identity called the super Jacobi identity, where again, we're multiplying by these factors of -1. Under these axioms, we can regard G1, so the odd portion, as being a G0 module, equivalently a big G0 module, where little g is just Lie of G0 via the adjoint action. So we're just going to send X to the X bracket. Right. So as a first example, we're going to look at GLMN.
David, just 1 second. We only see the first page online.
Says your screen sharing is paused.
Oh, yeah. Let me see if I can fix that.
Okay, that's better.
I see, but when I do the full screen, it stops.
Just hit resume.
Okay. Huh. Okay. Yeah. Okay. Okay. And then you can see that now. Is
Yeah.
everyone online able to see that?
That's fine. That's good.
Okay. All right. So now we're going to define what the Lie superalgebra cohomology is. So if we let G be a Lie superalgebra, we're just going to define the cohomology groups Hn of G comma M to be the cohomology of the cochain complex with cochain groups given as follows. So Cn of G comma N is just going to be the Hom set from the superior exterior algebra of degree N on G to N, where the superior exterior is essentially a direct sum over all I plus j equaling N of the exterior of degree I on the odd even portion, tensored on the symmetric of degree j on the odd portion. And the differentials are essentially the same as the differentials for the Koszul complex for the ordinary case, again, just with these factors of -1 in the bracket. Right. So in 2008, work by Bo, Fujawa, and Nakano defined what's called a detecting subalgebra. So if we let G be a classical Lie superalgebra, there's two potential actions that G0 might admit on G1. One is called stable and the other is called polar. So if G admits what's called a stable action, then there's going to exist a subalgebra F, a direct sum of F0 and F1, which is going to be isomorphic to a sum of copies of, actually, I'm sorry, I think I skipped a slide here. Yeah, I'm sorry about that. Yeah, so if we just want to go back for a second, if I look at all of the Lie superalgebras, these are going to be, first of all, GLMN, the set of all M plus M by M plus N matrices, where in the top left and bottom right quadrants corresponds to our even portion, and the top right and bottom left correspond to the odd portion. SLMN is just going to be all matrices of supertrace 0. And then we have an analog to essentially SO and SP from the ordinary case. And then we have a series of exceptional Lie algebras, and then two other series called QN and PN, and then Cartan type Lie superalgebras. And all of these together are going to comprise what are essentially the simple Lie superalgebras under consideration. And these aren't all necessarily simple, but they're simple enough for the calculations that are going to follow. And so back to that. So SL11 is just elements of GL11. So they're essentially going to be 2 by 2 matrices with a super trace of 0. And what we're saying here is that for G admitting a stable action, then there's going to exist some subalgebra F that's isomorphic to a direct sum of copies of SL1. And what's going to happen with this particular subalgebra is that if I look at the relative cohomology of G comma G0, well, this is going to be isomorphic to the cohomology for this subalgebra, this in general much smaller subalgebra F comma F0, as long as we're looking at the fixed points under this reductive group N, which is dependent on what F is. Similarly, if G admits this other type of action called a polar action, then there's going to exist some subalgebra E, which is going to be isomorphic to a direct sum of copies of this other subalgebra Q1, such that this restriction map, where WE is a pseudo reflection group, again, dependent on E, is an isomorphism again.
N come from?
N is just it's a reductive group. I think it comes from the like the normalizer of like specific semi-simple elements in G1. Yeah, so it's really.
It's part, is it like part of the data of this app? Or?
Yeah, it's part of the data of where the F comes from.
Okay.
Yeah, so like the N and the WE, they are part of the data for both the F and the E. Yeah, so a stable action is really if we just look at the action of like G0, so the group corresponding to little G0. Essentially, we want to see if like the set of points that are like closed, whose like orbits are closed, if that forms like an open dense set, that's going to be a stable action. It's polar. I think it's essentially polar if like the orbits are yeah. Okay. Yeah, but if we look at these detecting subalgebras E and F, supposing G is a classical superalgebra with both a stable and a polar action, then in general, what we're going to have is that E, the one corresponding to the polar actions, a subalgebra, the one in the stable action, which is a subalgebra of G, and we have this isomorphism of rings down here. Again, where N and WE correspond to the reductive and the pseudo-real factoring groups for F and E. And this is really just an analog of the Chevalley restriction theorem in the organic case. All right. So as an example of what these would look like, in the case of like GL32, or really in any of the GLMN cases, the odd portion of this detecting algebra is going to be essentially just the main diagonals in each of the odd quadrants, whereas the even portion is really just going to be F1 bracket F1. And so in this case, it's just going to correspond to mostly the main diagonal in each of the top left and bottom right quadrants. Right. So in addition to the notion of a detecting subalgebra, BBW parabolics were introduced by Grantcharov, Nakano, and Wu in 2019. And essentially what these are going to be parabolic subalgebras that for which an analog of the BBW theorem from the ordinary case holds for superalgebras as well. And so if G is a classical simple Lie superalgebra over C and F is detecting subalgebra, then there's going to exist this parabolic subalgebra B, which is going to be F direct sum this other subalgebra N, such that we can find this triangular decomposition N minus direct sum F direct sum N plus. This B is going to be called the BBW parabolic subalgebra. And essentially what's happening here is just as in the ordinary case, we have a triangular decomposition to the torus, positive roots and negative root spaces. So too, we have a direct sum decomposition into the detecting subalgebra F and essentially analogs to positive and negative weights. And what they did in GG and W was essentially compute the cohomology groups for the trivial module. And that's essentially the etymology of the BBW term. All right. What these would look like, though, is, again, just like in the case of GLNN, where the Borels are just going to be the upper triangular matrices. So to here, we can see that the Borels defined by GG and W are just going to be the F terms, so the main diagonals, along with upper triangular matrices in each of the four quadrants. Right. Now, recent work by Nakano and Wu has also been done on constructing a category LF, and they've proven an analog to the X isomorphism that I've mentioned before. It remains, however, a fundamental problem to compute these Hn of n plus, comma, L lambda groups and determine if there's a Constantine formula for LF in general. So this would be the analogous problem to determining the Hn of U, comma, L lambda for the ordinary case. And so in general, this is going to be a much more difficult problem than in the ordinary case because modules over a superalgebra are in general not completely reducible. And so figuring out the formulas for how to calculate these is rather difficult, but the calculations below are going to provide the first steps towards solving this problem. All right. So how I'm going to do that is, well, if I is an ideal of a superalgebra G, then we first of all get a short exact sequence, 0 to I to G mod I to 0. And just like in the ordinary algebra case, this is going to give rise to a Hochschild-Sayre type spectral sequence where the second page E2, Ij, is just equal to the ith cohomology of G mod I, comma, the jth cohomology of I, comma, C. And this is going to converge to the I plus jth cohomology of G, comma, C. Now, as it turns out, for each of the infinite families, GLMN, OSP2M2N, OSP2M plus 1, 2N, and QN, you can find an ideal I of the subalgebra N such that this corresponding spectral sequence ends up collapsing on the E2 page. So essentially, it'll just end up being a direct sum of each of these IJ terms. So as an example of how this would work in the case of GL33, well, the subalgebra N is going to consist of all matrices that are strictly upper triangular in each of the 4 quadrants. And then I, the ideal that we're interested in, is just going to be the matrices whose non-zero entries are in red. And so essentially, that's just going to be the rightmost column of each of the 4 quadrants. All right. Now, N is going to end up decomposing as a direct sum of weight spaces under the action of the maximal torus of G, by which I mean the maximal torus of the even portion. And so if we let epsilon I and delta J just be a dual basis to each of the entries in the torus, so E1 essentially corresponds to the entry E11 up here, epsilon 2 corresponds to E22, epsilon 3, delta 1, delta 2, delta 3. Well, we can split up N into a direct sum of weight spaces as shown here. Right. Now, we're going to let EIJR be the corresponding spectral sequence that comes from modding out by this ideal. Now, since EIJ2 is just going to equal the ith cohomology on N mod I, comma, the jth cohomology on I, comma, C, each subsequent EIJR is going to be a subquotient of this. And this is in turn a subquotient of the super exterior on N mod I star, tensor the super exterior of degree J on I star. And this really just comes from the definition that we were using from the cochain complex for cohomology. Right. Now, the differentials dr are going to have by degree r comma 1 minus r, and so they're going to send EIJR to EI plus r comma j plus 1 minus r. Right. So they're going to respect the action of the torus, and so they're going to send weight spaces to weight spaces. However, if we look at what the weights in here are, well, this is going to consist of a sum of I copies of weights from the black region, whereas the lambda JS of I star is going to consist of j copies of weights from the red region over here. And such weights, since each weight here contains an epsilon 3 or a delta 3, is going to contain teradodal copies of epsilon 3 or delta 3, because none of the weights in black consist of those terms. All right. And so since the differentials are sending ij to I plus r comma j plus 1 minus r, and at least when r is greater than or equal to 2, j is not equal to j plus 1 minus r, there are fewer total copies of epsilon 3 and delta 3 in the image than there were in the pre-image. And because of that, there's going to be, the differentials have to be 0 because they're sending weight spaces to weight spaces. And so that's going to force the spectral sequence to collapse on the E2 page. All right. Any questions about anything before I move on? All right. So with that in mind, we can start trying to calculate the cohomology groups, at least in small cases. It'll turn out that for the H1 cohomology, we don't quite need the spectral sequence just yet. So if we start off with a definition of a super derivation from a superalgebra G to a G module M as being a linear map phi, such that phi essentially preserves the bracket. So phi of xy is going to equal x acting on y minus -1 to the xy times y acting on phi of x. We're going to have that an inner super derivation is just going to be a derivation of the form phi sub a of x, just equaling x dot a for some a and n. So essentially, these are the analogues to a derivation and an inner derivation for the case of ordinary Lie algebras. And just like in that case, we have the following result, where if we want to compute the first cohomology, G comma M, well, this is going to be isomorphic to the set of super derivations modulo the set of inner super derivations. And the proof is completely analogous to how you would show that for the ordinary case. Right. Now, when m is equal to c, we can simplify this considerably. So if we want to compute the first cohomology of G comma C, well, this is just going to be isomorphic to G mod G bracket G star. So again, this is really just like the ordinary case, and computing these is generally not too big of an issue. All right. Computing the second cohomology, however, tends to be a bit more difficult. So in this case is when we're going to start using the spectral sequence. Now, to begin with, we're going to start with the simplest case where we're looking at GL22. And so n in this case is just going to consist of matrices of the form like here, where we're just looking at a potential entry in each of the top right corners of each of the quadrants. All right. And so if we look at the multiplication for n here, it's going to turn out that n is abelian. And because it's abelian, if we go back to the chain complex for computing the cohomology, it turns out that all the differentials are going to be 0 in this case. And because they're all 0, it'll just collapse. And so the second cohomology is just going to be congruent to C2, which is just the supersymmetric of degree 2 on n star. And so we can see what the weights are going to be. They're just going to be sums of 2 weights of n, where any even weights that we're including are distinct. And this is in total going to have dimension 8. All right. Now, what we're going to do in general is that if we look at the collapsing spectral sequence and just want to look at the H2 term, well, it's going to turn out in this case that we can see that H2 of n comma c is just going to be isomorphic to this direct sum of H2 of n mod I comma H0 of I comma c, direct sum H1 of n comma mod I comma H1 of I comma c, and then direct sum H of 0 of n mod I comma H2 I comma c. All right. And moreover, since I is going to be abelian, it was just the rightmost columns in the G3 case, or really in any GLMN case. Since it's going to be abelian, these terms again are just going to collapse and they're going to be isomorphic to the super exterior of degree J on I star. Right. So now what we're going to do is let just n sub k denote the nilpotent radical of G equals GLKK. Right. So then we can just rewrite the cohomology as such. And since n sub k mod I is going to be isomorphic to n sub k minus 1, so in this case where I'm looking at GL33, if I mod out by I, what I have left is really just going to be isomorphic to the n coming from GL22. This is going to enable us to essentially compute the cohomology recursively. All right. So we have those 3 terms that we want to compute. The first term is just going to be the n3 mod I comma c, which by the recursion is just going to be isomorphic to H2 of n2 comma c, which from the base case we saw had dimension 8. The third term, so the H0 of n3 comma I mod I comma lambda 2 of I star, well, this is really just going to be the fixed point set of lambda 2 of I star. And again, it's not too hard to show that this has dimension 8 as well. The middle term, and this is going to be the hardest term to compute in general, to figure out how or what size this has, we can compute this by hand, looking at the kernels and images in the chain complex. So if we're looking at the GL33 case, here are the first few terms in the cochain complex for its cohomology. And so essentially we're trying to see what appears in the kernel of D1 modulo the image of D0. And so really it's going to turn out that this is going to be equivalent to figuring out which weights appear in here but not in here, modulo which weights appear in both here and here. Right. So the image of D0 is going to turn out to correspond to weights of I star that are also weights of n mod I star tensor I star. And it's going to turn out that those are just weights that are in the top right corners of each of the 4 quadrants. So epsilon 3 minus epsilon 1, delta 3 minus epsilon 1, epsilon 3 minus delta 1, and then delta 3 minus delta 1. Right. And so that's going to be a total of 4 weights here. The kernel lever is going to correspond to weights that are in here, but not in here. And again, these are just going to correspond to essentially sums of black weights plus sums of red weights that aren't in the top right corners. So there's going to be a total of 4 times 4 such weights, which will give a dimension of the kernel of being 16. And then this is just going to have dimension of 16 minus 4 is going to have dimension 12. And then the way that we're doing this also allows us to just keep track of which weights appear. And so the dimension is going to be 28, but we can keep track of like which weights were actually included and excluded in this. And so this is going to enable us to write what the cohomology is as a direct sum of weight spaces. And really, this procedure can continue for higher and higher dimension as well. So if I want to do GL44, well, I can do the same sort of thing now that I know what GL33 is, and then the same for GL55 and so on. And then this works for the other families as well. The ideal when you quotient out by it, you're just going to get something smaller, and then that'll enable you to work up recursively. Right. Are there any questions about this before I move on? Right. So the second part of my talk is going to be on some sheaf cohomology theory. So we're going to let G be a supergroup and B be a BBW parabolic subgroup, and we're going to let LF of lambda be an irreducible representation graph. Right. We're going to define the sheaf cohomology groups Hn of lambda to be the higher right-derived functors, just Rn, of the induction functor from B to G of L sub f of lambda. Right. And now the cohomology groups Hn for the trivial module, so where lambda is equal to 0, were computed in GG and W in terms of the Poincare polynomial for the odd vowel group. Right. So in computing some results, we're going to make use of the following 2 spectral sequences. So this first spectral sequence, which I'm just going to call henceforth spectral sequence 1, was inspired by work of Sam, Snowden, and Brundon. And what it says is that if G is a supergroup scheme and H a closed subgroup scheme of G, with little g just being the Lie algebra of G and H being the Lie superalgebra of H, if M is an H module, then there's going to exist this spectral sequence with first page EIJ, just being the I plus Jth right-derived functor of induction from the odd portion, from the even portion of H to the even portion of G, of M tensor lambda J of G1 mod H1 star. And this is going to end up converging to R of I plus J of just induction from H to G of M, restricted down to G0. So essentially over here, we're having just regular or ordinary algebraic group sheaf cohomology, and then the same over here. But then this is really just the sheaf cohomology for the supergroup, just restricted down to G0. And where this comes from is essentially just the spectral sequence construction emerging from a filtration. So what we're going to do is if M is an H module, and we let just this be an injective H resolution of M, right? Tensoring by KG, we obtain an injective H resolution for M tensor KG as well. And that's going to be as follows. Right. Now we can filter KG by powers of this subgroup I, which is just equal to KG times the odd portion of KG. And this is going to induce a filtration on these CN groups, which are going to be the induction from H to G of just IN tensored KG. And so we're just going to obtain a filtration of CN like that. All right. Now, since these IN are going to be injective, if I look at the H1 of just H comma IN tensor IK, with I being injected, those are going to end up being 0. And so if I just look at the corresponding short exact sequence for H0 of H comma IN tensor IK mod IK plus 1, it's going to turn out that this is just going to be isomorphic to H0 of H comma IN tensor IK mod H0 of H comma IN tensor IK plus 1. And so this is really just the quotient of core consecutive terms in the filtration for Cn. And so we're going to get that this is really the E0th term corresponding to like ij in the spectral sequence. And so from Kumar, just following that spectral sequence, we're going to get this spectral sequence with first page just being hi plus j of h comma m tensor I to the I mod I plus 1, converging to the cohomology of h comma m tensor kg. Work by Brunton, however, shows that this first term here is actually isomorphic to just the ith plus jth cohomology on the even portion h0 comma m tensor symmetric of degree j on g1 mod h1 star tensor k of the even part of g. And so putting this all together just gives us the spectral sequence from before.
Do you really intend that to be hi plus j for the?
Yes. You mean right here? Yeah, that should be I plus j for the first page. Yeah.
So yeah, you don't really expect each I, then ij mod ij plus 1.
Yeah.
But it's not each I and then ij mod ij plus 1.
No, it really should be the I plus j and then I mod 1.
That's pretty. I guess come on, it's kind of standard. You can try to rewrite this.
And then in addition to that spectral sequence, we're also going to have a second one, which I'm just going to call spectral sequence 2 from now on. And it's analogous to that found in Janssen. It really is just a Grothendieck type spectral sequence coming from the composition of two induction functors, one from H to K, and then one from K to G, where H is contained in K is contained in G. And just like in the ordinary case, we have that the composition of these right-derived functors is going to converge to just R of I plus J of induction from H to G of N. Right. So using the first spectral sequence for now, we can start to prove an analog of Kempf's vanishing theorem. So recall what Kempf's vanishing theorem says in the case of ordinary Lie groups. So if G is a reductive algebraic group, B a Borel subgroup, and lambda is a dominant weight, then it's going to be the case that the higher cohomology groups, hi of lambda, are going to equal 0 for all I greater than 0. So they're going to vanish for non-zero I. So as long as our weight is sufficiently large, we're going to be able to prove an analog for the supergroup case as well. So to do that, we're going to define what's called a very dominant weight. So if lambda is just a weight, and then W is an element of the even vol group, we're going to say that the weight lambda is very dominant if mu plus sigma is also dominant for all mu that are weights of L of lambda, and then for all sigma that are weights of the exterior on G mod B star. And then if you go and analyze what this actually means, well, this is just going to correspond to sums of distinct negative roots of G for sigma. And we're going to denote the set of very dominant weights by x x plus plus. And then if we set gamma to be lambda comma W, just to be the weight space of alpha lambda tensor W inverse applied to the exterior. And we'll just let for any little gamma in this set, we're just going to let m of gamma comma W just be the multiplicity of the weight gamma in this module. Right. So with this all in mind, we can give a criterion for when the higher cohomology groups vanish. So if lambda is very dominant, and we'll let 1 be the identity in the even vol group, then it's going to be the case that the higher right-derived functors of induction from B to G of L lambda are going to end up equaling 0 for all n greater than 0. And then it will also turn out that if we just look at the restriction of the induction of L of lambda down to G0, well, we can just write this as a direct sum over all weights gamma in big gamma of lambda comma 1 of induction from B0 to G0 of gamma, direct sum with a number given by the multiplicity. And really why this is the case is if we just go back to what the first spectral sequence was, we're just going to write that H as B and then look at our modules being alpha of lambda. And then the definition of being very dominant was specifically constructed so that all of the EIJ terms were 0, except for when I plus j equals 0. Okay. In addition to that, we also have a result that's an analog of the Parabolic theorem. So recall what this says over a field of characteristic 0 for an ordinary or an ordinary algebraic group. So if we let CZ bar denote just the set of all lambda in X, such that 0 is less than lambda plus rho, comma, alpha check for all positive roots alpha, where rho is denoting the half sum of positive roots, and let lambda just be some weight that's in CZ bar. Well, first of all, if lambda is not dominant, then Hn of W dot lambda is equal to 0 for all n and for all W and W. And then if lambda is dominant, then we're going to have that Hi of W dot lambda is going to be isomorphic to H0 of lambda, provided I is just equal to the length of W and 0 otherwise. So again, we're going to define what it means to be properly large in this context. So we're going to define generic weights here. So we'll set omega of W just to be the set of all lambda, such that for all mu that are weights of alpha lambda, and all sigma that are again going to be sums of distinct negative roots. So an element of here. We'll say omega W is the set of all lambda such that mu plus W inverse sigma is in CZ bar. And then we'll say a weight is generic if and only if it's in the union over all W in the even vowel group of W dot, and this is going to be the dot action again, omega of W, which we'll just say is omega. And then the set in total, we'll just call the set of generic weights. All right. So just like before, we can say that the Parabolic theorem holds for generic weights. So suppose that W dot lambda is a generic weight where lambda is in a omega W. Then if we look at the restriction down to Z0 of the nth higher right derived functor of induction from B to G of alpha W dot lambda, well, if n is not equal to the length of W, then these are just going to be 0. And otherwise, they're just going to be a direct sum over all gamma that are weights of that. Again, with multiplicity and gamma W. And again, the definition of being generic was specifically constructed so that all the terms of interest in the spectral sequence were 0. Right. So in addition to that, we may be interested in just figuring out which weights in particular are generic. And we do get some nice results for what these would look like. So we're going to start off just with a simple lemma, which says that if G is a semi-simple Lie algebra and sigma a sum of distinct negative roots of G, meaning it's going to be a weight of the exterior on G mod B star. Then for all W in the Weil group, we're also going to have that W dot sigma is again a sum of distinct negative roots.
I'm sorry, what if W is the one you saw in the Weil? If W dot sigma is positive.
So that would be W on the regular action of W, right?
Oh, you think W dot?
Yeah, so this is specifically the dot action that I'm referring to. Yeah, as long as we look at the dot action and that doesn't happen, it still sends distinct negative roots to distinct negative roots again. Based on this, we have the following result, where as long as G is just equal to Qn, then it turns out that the generic regions, so the ones defined before the W dot omega W, are going to be conjugate under not the dot action this time, but the regular action of the Weil group W0. And so consequently, we can say that omega is just going to be the union over all the ordinary conjugates of just omega 1. And roughly how we can see that is it's just going to be enough to show that W dot omega W is equal to W of omega 1.
Couldn't it be true that between SL2, couldn't it be true that if you took W, the simple reflection dot of one negative, you don't get 0?
But we're going to treat that as just a sum of distinct negative roots still. Yeah, that'll just be like the null set.
Then you solve it.
Right. So if lambda is in omega 1, then for all positive roots alpha and all sums of distinct negative roots sigma, well, by definition of it being in omega 1, we can write this as a statement that lambda plus sigma plus rho alpha check is greater than or equal to 0. All right. So that's just what it means to be in omega 1. By the above lemma, however, that the dot action applied to a sum of distinct negative roots is again a sum of distinct negative roots. This is going to force that, again, by definition of being an omega 1, lambda plus W inverse dot sigma plus rho comma alpha check is again greater than or equal to 0. And then just manipulating this expression somewhat, we can rewrite it as just lambda plus W1 inverse rho minus rho plus W inverse sigma plus rho. And so based on the definition of omega of W, this is going to force lambda plus W inverse rho minus rho to be an element of omega W. This, however, if we just look to see what this is going to be equal to omega inverse dot omega W with the regular action here. And so that means omega W lambda is going to be in W dot omega W. And so we have this inclusion here, and the other direction is going to follow similarly. And so what this is going to mean is that all of the other generic regions, the W dot omega W's, will just be conjugate by the regular action to omega 1. So giving some examples in small cases. So first of all, with Q2. In this case, the even Weil group W0 is just going to be the symmetric group on 2 elements. And so all the sums of distinct negative roots will just be 0 and minus alpha in this case. And then we can just really directly show here that omega 1 is just going to be the set of all lambda equal to lambda 1 comma lambda 2, such that lambda 1 minus lambda 2 is greater than 1. And then similarly for omega of S alpha is just going to be the set of all lambda 1 minus lambda 2 greater than or equal to negative 1. And then if we apply the dot action, our generic weights in this case just end up being all mu such that mu1 minus mu2 is not equal to 0. And the results that we can compute based on this are really just the same as the calculations that Brendan had given in his paper on Q and cohomology. Extending this to Q3 now, well, in this case, the even Weil group is just going to be isomorphic to the symmetric on 3 elements. And we can work out again that the generic regions, the omega of W's, will be all of these satisfying, all the weights satisfying the conditions listed. And then if you apply the dot action of W on omega W, you'll see that these are all conjugate. Actually, if we just draw it here, plotting all 6 regions omega, or I'm sorry, W dot omega W, we get these 6 different conjugate regions here. So this would be 1 dot omega 1, and then the others would be as follows. And they'll all be conjugate under the regular action.
Sorry, so you should not, so omega is a shaded region.
Yes. Yeah, so I'm sorry, yeah. Omega 1 is the shaded region. And this would be like S alpha 1 dot S alpha, omega S alpha 1. This would be S alpha 2 dot omega S alpha 2. But they all end up being conjugate under the regular action instead. All right. And so the last thing I wanted to talk about today was just some calculations for the sockles of these H1 lambda terms.
Maybe you can map it.
Okay.
So from that picture, maybe you can explain, like, you take the sheaf cohomology. So it's known by the BBW theorem in the sheaf.
Right.
So what about the other regions?
So for the other regions, it's not quite known yet. I mean, it's known for 0 because that comes from GG and W. All the cohomology terms that we give for the trivial weight. But beyond like the generic regions, so the ones all shaded in gray, these white regions here, they're still open. Like it still remains to be seen, like even like when they're not vanishing.
Can I ask you to study
Huh?
other things like the translation functors and category O, like the wall crossing functors?
I haven't really thought too much about like what those would be in this context. Would there be translation functors in this? Yeah, it's still kind of open.
This theory is kind of inconsistent.
So finishing off with just like computing the sockles for H1 of lambda. Recall that the socle of a module M is just going to be the sum of all of its simple submodules. And so in the case of reductive groups, H1 of lambda is always going to have a simple socle as long as lambda is dominant. But this ends up not needing to be the case for supergroups. So as an easy example of that, if we just consider the case G equals Q3, then by GG and W, the H10 is just going to equal C direct sum C. And so the socle is going to be everything in this case, but it won't be simple.
So lambda is not dominant.
Lambda is not dominant. Yes, sorry about that. Yeah, as long as lambda is not dominant. So if we let X of F plus just be the set of all highest weights lambda of irreducible F modules, so F is what restricts down to the detecting subalgebra F, such that H0 of lambda is not equal to 0. And we let P just be LP semi-direct product UP, just be some parabolic subgroup containing the BBW parabolic B. For any sigma in X of F plus, we're going to let sigma bar just be the corresponding weight in X, where LP of sigma bar is just equal to the fixed points under UP of L of sigma. And using the second spectral sequence 2, we can prove the following result. So if G is a supergroup arising from some simple Lie superalgebra G, B a parabolic, and then P is a parabolic containing B. Suppose we also have that the induction from B to P of L of lambda is equal to 0. Then in this case, it's going to be the case that the index of L of sigma in the G socle of H1 of lambda is going to be the same as the index of LP of sigma bar in the socle of R1 of induction from B to P of L of lambda. And so from that result, we obtain the following criterion for simplicity. So as long as we have that parabolic scheme such that the induction from B to P is 0, but then the induction or the R1 of induction from B to P of L of lambda has simple L socle, then it's going to turn out to be the case that the G socle of H1 of lambda is simple, just based on that criterion from the different indices. So if we look at what happens in the specific case of Q2, suppose we have G as Q2 and let sigma be sigma 1 comma sigma 2, just be some weight. A result from Pankov actually computed what the formal characters of all of the irreducible Q2 modules are. So if sigma is not an integer multiple of rho, then the formula can be just given by all these conditions here, where this L sub 0 sigma is just the irreducible G0 module of highest weight sigma. So really this is coming from like GL2 theory, what this character should be. And then if sigma is an integer multiple of rho, well then it's going to turn out to be the case that the character of lambda of L of sigma is just twice the character for the ordinary case. However, in addition to this, work by Brunden computed also the characters of the induced modules from B to G of alpha of sigma. And it turns out that their formula can be given as follows here. So 2 times E of sigma plus 2 e to the sigma minus alpha and so on. And so based on that and what the characters of the irreducible modules are, we're going to have that as long as sigma is not an integer multiple of rho, with this added condition that sigma 1 is not equal to sigma 2 plus 1, then the induction from B to G is just going to be an irreducible module isomorphic to L of sigma. And so based on this and using an analog of serial-duality for supergroups, it'll turn out to be the case that H1 of sigma is either going to be 0, irreducible, or is going to have a Sockle isomorphic to L of W sigma minus alpha. In any of these three cases, it's going to be the case that the module has a simple Sockle. And so based on that, if we let now just G be Q of n, and P sub alpha be a minimal parabolic subalgebra, isomorphic to L alpha semi-direct UA, suppose we have some lambda in X with lambda comma alpha check just being less than 0. Well, using the above theorem, and it can be shown that we have this equivalence of indices L of sigma in the G Sockle to L sub P alpha sigma bar in the alpha L alpha Sockle here. And by the above, it's going to turn out that these modules here, these R1 of induction from B to P alpha, L alpha lambda, have to have simple LA Sockle. And so this leads to the following result for all Qn. So suppose we have that lambda comma alpha check is less than 0 for some alpha, then it's going to be the case that H1 of lambda has a simple G Sockle. Right. Now, I guess some open problems would be from the first section, just to compute what these Hn of NC are for n larger than 2. This recursion idea that I mentioned at the beginning, it could possibly be extended, but the higher and higher degree you go up, the more computationally complex it gets. Additionally, for these sheaf cohomologies, what remains to be seen would be like computing when the G Sockle is simple for not Qn, but GL2 too. So really all our results right now are just for the Qn case. Extending to even like GL2 would be an improvement on that. But yeah, I think that's everything I wanted to say today. So I'd like to thank you very much for listening, and I think I'll just stop there.
Okay, so since there's no question, then let's again thank David.
I think the procedure of the committees and David picked, and everyone else,
Recording.
You might want to just exit out of here, like just.
Yeah. Or let me just. Yeah, let me just.
And then yeah, just.
Stop.